Here we are. Hello, everyone, from our virtual new studio in Midwest Machinery. I am Brian Gomsky, Director of Marketing and Business Development.
And I'm Aire, outside sales engineer.
Talk close to that.
Aire, outside sales engineer.
So we're pretty excited about this presentation today. You probably saw in our messaging, we've actually, along with Paul, gave this presentation at Missouri's largest medical cannabis expo earlier this year. I got a lot of great feedback about it. So people who couldn't attend wanted to make sure we could get this to you again.
We also did a similar one at our local Aire as well. So if you attended that, you'll see some similar information in it.
So we're going to go ahead and introduce Paul Stewart, who is an industry veteran and expert in all things HVAC and grow room related air quality. But Paul, why don't you go ahead and I can't do enough honors for you. So why don't you go ahead and introduce yourself?
Okay, well, very good. Well, thanks, guys. I appreciate you having me on the screen here today, and hopefully we'll give everybody a few good nuggets to take away as they get into the legalization of cannabis in the state of Missouri and start doing their build-outs. I'm with Desert Aire. I've been the Vice President of Sales over here for the past, I'm in my 12th year. Prior to that, I did 23 years with Johnson Controls in a variety of management positions, most notably in equipment. Control sales to equipment manufacturers has been my background. So that's pretty much my background. I've got an engineering degree from the University of Illinois across the state. And, I've been involved in HVAC equipment for the past 30 some odd years. I'm a member of Aire, the American Society of Heating, Refrigeration, Air Conditioning Engineers, and I've also served on a couple of other entities in the industry, such as the Model Aquatic Health Code, to name one. So what we wanted to do today is really kind of give you guys a overview of what you need to do and what you need to be thinking about as you get permitted and you're headed down the path of looking to make a successful and profitable cultivation facility. So, we'll give you a congratulations to begin with. You guys won a license. If you're sitting in the room, you may have got your permit. Pardon? Shout out.
Just telling them good job. Yeah.
There you go. So you really got, I'll say, part of the hard stuff out of the way. I know it's always been a challenge, and as we've done this across the country now, I think we've got about 33 states that are medicinally legal. We've got 11 states that are recreationally adult use legal. And, every state is kind of their own fiefdom, and some of them also seem to be a little interesting on how they do issue their permits. So like I say, you made it through that first milestone and moving towards the legal cannabis trade. So, the next thing here is, okay, you've gotten through that particular piece. A lot of application work. You've had to put together your team. You've had to find funding. And, but one of the things we want to make certain is, as you put your business plan together, here's a very interesting fact that continues to happen across states that become legal. At the beginning of the legalization process, the price per pound for finished product tends to be high. And as the growers and cultivators come online and we get an increase in supply, and additionally, as the demand for product tends to level out. I mean, there's not an insatiable demand for cannabis consumption. Just look at what's happening in Canada right now. They have built out a significant amount of growth up there for cultivation. Part of it was the intent to export that product, and you've got people laying 40% of their staff off. You've got folks determining whether they're going to sell off a couple of different operations just to raise capital and keep things moving. So just because you grow it doesn't mean you're going to be successful. You have to make certain that you take into consideration that over time, your price point is going to drop. The slide I have up here right now is What's happened in Colorado since they legalized for adult use back in 2014? At the onset, wholesale product was going for about $3,000 a pound, and now it's down at about $1,000 a pound. Now there are three different price points there. You've got a price for outdoor grow, which is the lowest. You've got a price for greenhouse grow, and then you do have your highest price product, which is your highest quality, your best yield, maybe more consistent product is going to be your indoor grow. So there are three price points there, but keep in mind that you will see a decline in what you can get for your product as people come on board and supply increases and demand flattens out.
Paul, that's like one of the big things that we're kind of talking about here too, is it's the profitability portion of it, right? I mean, anybody can, throw equipment at it to, make a system, work okay, right? But it's
Right.
Really diving into why this, what we're going to be presenting is more effective and more critical for this, because that's exactly what that slide shows. It's, yeah, everybody's profitable in the beginning, but it's how do you sustain
Right.
long term, and how do you be profitable without having to basically redo everything that you've done in the onset?
Yeah, I think that what you have to think about is, do I want to be in business in 5 years? Am I doing this for a short-term gain, or am I doing this to be in business in the long term? And I would hope that everybody looked at it as, yeah, I'm looking at this and being in it in the long term. And if that's the case, take a longer look view and make sure you understand what may occur. If you built your business model on being able to sell product for $2,000 a pound, you may be okay for a few years, but what happens when the price point drops to $1,500 a pound and you're having to sell it for below your costs? You can't continue down that path. I know there was an electronics guru years ago that we always used to kid, how can I afford to sell to you below my costs? Volume, volume, volume. Well, that doesn't always work. It's a great tagline, but yeah, that's not going to pay the rent long term. So keep in mind, what we're trying to give you is we want to help you think about what you need to do to have a successful long-term operation that has operating costs in mind as well as first costs in mind. You can't just buy the cheapest thing out there and hope that that's going to sustain you through a time period.
Right.
So, on this next slide here, a lot of issues that you're going to have to kind of keep in mind. Utility bills will be one of your biggest expenses. And when you talk about utility bills, you're talking about electricity, you're talking water, you're talking sewer, potentially gas. That needs to be taken into consideration. And, your operating costs should be part of your equation. We tend to go through this equation with folks all the time. Guys will come in and say, well, I'd love to buy your Desert Air equipment, but you're 20%, 30% more expensive than what I can buy over here with, these air conditioners and portables. But what they fail to realize is the operating costs of the portables and the air conditioners are going to be 30 to 40 to 50% more expensive to physically operate to do the same work. So, we just did some analysis for a grower the other day, and the payback for my increases in first cost, the payback was about a year. And yeah, I mean, that was significant because they were trying to figure out, well, we've always done it this way, and we've always gone with the lowest cost equation up front and make it work. And that doesn't even take into consideration the increase in yield that you may see by being able to control the environment to the ideal operating and plant growth environment. And so as we talk to growers, when we start talking about the impact of maintaining that environment, are you able to get 5% greater yield by controlling to a tighter environment that you desire? Are you able to get 10%, 15%? What's that worth? And I know that part's a little harder for someone to understand up front. All they look at is, hey, this costs this, and this costs this. Think about those other aspects. And I think the other thing that we're pointing out in this slide here is, if you don't maintain the environment properly, you will have things that can just decimate your entire operation. You know, mold and mildew. If you get that in your crop, then it's tough to get rid of. It can consume an entire room, and in most states, the way to mitigate that is if it gets inspected and it gets deemed that it's unacceptable, you're effectively just, you know, it turns into scrap. You're having to discard it. So there are some ramifications that come into effect when you can't control the environment and keep a good environment there. All right, so obviously what we're trying to get you to is to think about what's happening in the room, what are the loads, what's the proper equipment. You know, I always say, you know, don't bring a knife to a gunfight. You know, if you know you got a battle here, bring the right equipment. And, you know, just because something's cheap or just because something looks like it might be right, doesn't mean it may work for you. So get a properly designed system, get your, you know, and we recommend you get an engineer involved. You're going to have a mechanical, electrical and plumbing stamp for your facility. So get them involved early, but also you got to make sure that you know enough about what the application's about so that if they are not educated in this type of an application, they don't make a mistake. I mean, I know engineers, you go back, you know, 6, 7, 10 years ago, engineers thought it was a lighting issue. The heat from the light only is what they had to account for. They didn't think about what plants do. So, you know, that's going to be the big thing is the more you guys know as the cultivation and the grower and even the finance person behind it, the better off you're going to be able to control your destiny with what goes in, what's going to be the most effective, and then how you sustain yourself going forward. Any comments there, Eric?
No, I mean, it's, you say a properly designed mechanical system, there's so many things to take into consideration with that. And that's, I mean, we're going to kind of dive into those. And like you said, it's the details that you don't know that can kind of really catch you. So.
Yeah. Well, I'll throw one out just from a utility standpoint that a lot of people are now starting to think about, and that's the water consumption. So, you know, most jurisdictions charge you your water. They put a meter on your water intake, and then they charge your sewer as a function of the water intake. What if you reclaim your condensate that comes off of your equipment? If the plants consume, let's just say, easy math, 1/3 of a gallon of water a day in the flower room, and you've got, you know, 300 plants. So now you're talking, you know, 100 gallons a day per plant. You've got several of those. And if you're paying for the water to come in to be used and you're discarding it all, you've got a pretty hefty bill there. What if you reclaim the water? The condensate that comes out of the dehumidification and the HVAC system, you reclaim that water and treat it, you can probably reclaim 70% of that water. And now that utility bill goes down. Now, I know 100 gallons doesn't seem like a big deal, but like I say, get yourself into a facility that's 10,000, 20,000 square feet, and you're going to be going through some significant water consumption. I mean, we've got our largest facility that we've done is 400,000 square feet under one roof. And that 400,000 square feet, they've got 38 or 39 flower rooms that have 1,500 plants each in them. I mean, that is a significant operation. You know, they've got a hefty water bill every month and sewer bill that goes along with it if they're not reclaiming that water and reusing it. All right, so as we move on here, so let's look at the loads, because I think this is, I know we've probably got some folks out there that aren't horticulturalists. They didn't study plant botany in college, and maybe they were the finance guys, and they looked at this as a good business opportunity. So let's do a little bit of background on, you know, what does a plant do, and what does a plant need to thrive? So if you look at plants, they absorb light, energy from the sun or the grow lights, and they bring up nutrients from the roots, water and nutrients. Water is actually used to pull the nutrients up through the roots and move it up through the capillary system in the stem and through the leaves to get it out there, where photosynthesis can go on. And I know I'm going back here to high school science class. That's probably the last time most of us have heard about photosynthesis, but photosynthesis occurs when the lights are there, and you're taking those nutrients and you're converting those minerals and nutrients to starches and such that the plant can use for growth. So it's growing its canopy. If it has a fruit, it's going to be growing that. In the case of cannabis, it's going to be at some point wanting to procreate and extend its life by either growing the flower if it's a female, or producing pollen if it's a male to pollinate the female. So obviously this is a no-brainer, but in the cannabis facility, we are only growing female plants because we only want to harvest the flower, and that is a female plant. So you got to look under the leaves and see which plant, what kind of genitalia they have, I guess. But there is a whole method out there for identifying the plant gender, and yeah, you're going to want to have female plants only. And this is another interesting aspect as you get into the hemp and the farm bill that was created a few years ago. If you have outdoor grows of hemp and you have some pollen that's being created because maybe they're doing seed generation or whatever, or they just haven't pruned back a plant that cut out one of the males in their field, pollen can float about 10 miles. So if you're bringing in a lot of outside air into your grow room, or if you're doing a greenhouse, you do have to worry about pollination from stray pollen. You may not have it inside your facility, but if it floats in, now you start having these plants, these female plants that's producing the flower. They got their sticky stuff to kind of grab that pollen and turn things to seed to extend the life, to produce the next offspring. So keep that in mind. But yeah, this is what the plants are doing. We're watering, we're grabbing nutrients down here in the roots. We've got our lighting energy, and the plant just goes through that photosynthesis process. And the majority of the water, we typically, in a flower room, 75% of the water is consumed during the lights on period when photosynthesis is going on. So again, another real big point to just be aware of. All right, so when we start talking about this indoor grow, we need to think about the loads. And as you talk to your engineer, and you try to decide, well, how much air conditioning do I need? How much HVAC do I need? How much dehumidification do I need? What forms of this are there? There are sensible cooling requirements, and there are latent. Latent is the moisture removal part. Latent is all about removing moisture. And sensible cooling is just temperature change. So the lighting load is your sensible cooling load. All those lights, whether they're LED or HID, they're putting off heat energy. A watt in equals a watt out. So however many watts are going into the room, that can be converted to BTU, and we can calculate, well, how much light energy needs to be offset by some sort of sensible cooling machine. So that's a real easy one. The evaporation, evapotranspiration is the actual form of that latent. And again, we have to account for that latent moisture removal that needs to happen in order for the plant to continue to draw moisture up. The minor loads, and these are going to be important, but we can negate these. For instance, the building's skin loss and heat gain. So what we're talking about there is it's the structure around. It's the structure of the building. If you're doing rooms within a room or rooms within a building and they don't have an external wall, then you can pretty much negate the effect of any skin loss or heat gain or heat loss through your room. If the around the building is at 70 degrees to 80 degrees and inside the room is 75 to 80 degrees, then there's no appreciable difference between what's going to happen from one side to the other. But if you've got an external wall and in the winter it's at 20 degrees outside, and inside the room you're trying to maintain 80 degrees, we will have heat loss through that wall. And again, that's where you have to account for it. So we just need to know about it. And you got to tell your engineer, hey, I do plan to have external walls. Therefore, we got to account for that heat loss and heat gain. Solar gain is very similar to that skin heat loss, heat gain, except it is the impact of sun hitting the wall and creating a radiant heat surface. So again, we negate that by having rooms within the building and not having any external walls. And again, if you think about the external walls, would I have greater heat dissipation or heat loss if I built my house out of a cardboard box versus built my house out of a brick outer skin, a 2x4 wall with injected foam insulation and then sheetrock on the inside? Which one's going to have more heat loss? Obviously the cardboard box house. So, all of that has to be taken into consideration if we're going to be exposed. And the same thing with the solar gain. If you have a lot of western part of the building, if all those walls that are exposed to the external wall, if they're all facing west, they're probably going to have more solar heat gain than a wall facing north, south, or even east. But again, your engineer can help you with that. And I say the best thing to do is just go with the walls within a wall. Go with the building with a room within a room.
Is that typically what you see then, Paul, is essentially a room in a room? I mean,
we do, because people want to, they're building out, a typical facility might have 4, 8 flower rooms. They might have 2 veg rooms that feed those flower rooms. You might have 1 mother room, 1 clone room, and then you've got some processing area. So you are already building those out because, if you think about it, guys are wanting to do maybe a different strain in the flower room, or in most cases, guys are putting the product in and it's spending 8 to 10 weeks in that flower room, and then you're harvesting it all. Well, you don't want to have just 1 flower room and harvest once every 10 weeks and then have it dry for another week and a half before you have product available. So guys will have multiple rooms so that they can be harvesting every week that they go along. So very typical. But yeah, the room within a room, we see a lot of it happening just because of this issue of their building rooms anyway inside the building. And people have come to learn that if I get it off of the outside wall, I can minimize the impact that's going to have on my room inside.
Right. We've seen typically here, locally, they're taking existing buildings, right? So how are you turning an existing building into an indoor grow facility? You just build something inside of it.
Yeah, the freezer panel walls are the primary method. It's a 4-inch polystyrene skinned wall, and guys can come in and put those up very, very quickly. You can also get that vapor barrier on the inside so that you're preventing any moisture migration as well. And that's important as well. You want a vapor barrier.
Right.
If you're trying to control what's inside the room, then make sure it's not seeping out somehow. Okay. And then the last one I've got down here, or we talked about infiltration a little bit, the vapor barrier. The other one is outdoor air ventilation. Now, I will tell you that if you run across any folks that come from the western half of the U.S., they have done some amounts of outdoor air ventilation to complement their HVAC equipment. And they can do that because they have a dry climate. In Missouri, Southern Illinois, we have humidity. Actually, everything east of this line that goes right down through the Dakotas, Nebraska, Kansas, Oklahoma, and Texas. There's this line that goes right down the middle of the country. Everything to the right of it has humidity during summer months, or at least some part of the year. And the further south you go, take the Gulf states, the lower Midwest, we got humidity for 4 or 5 months of the year. So, if you're bringing outside air in the middle of the summer when it's hot and humid in Missouri, how's that going to dehumidify your space? So we always say this is not a commercial building that is required to meet an ASHRAE 62 code ventilation requirement so that we don't choke on our own fumes. It's an industrial process. You have few people in there And oh, by the way, what do plants give off when they grow? They give off oxygen. So the oxygen content inside the grow room may be better than it is outside the grow room. So I would say, you know, we tell people this all the time on the eastern half of the country. You need to minimize your outdoor ventilation. You don't need it. And even out west, with this whole increase in outdoor hemp growing and even outdoor cannabis growing, how do you keep bugs, how do you keep pollen out of your facility? Well, if you open the windows and you're pulling in air, you now have to figure out, well, how am I going to mitigate bugs? How do I keep the bugs out? And how do we keep the pollen out? So correct. I mean, lighting adds heat to the room. I kind of talked about that on the previous slide. And again, it doesn't matter whether it's LED or HID. Now, one thing I will comment on with regards to your lighting choice, LED lights do operate with less energy to create the same light spectrum than a traditional HID. So that alone is a reduction in energy costs and could certainly help your operating cost impact. I think the other thing that people are learning is that HIDs have a large amount of radiant heat. I mean, you wouldn't want to hold your hand under an HID light for very long. You will burn it. Whereas an LED light, you can hold your hand under an LED light and you really, I mean, yes, there is some radiant heat, but it is not as intense. And the impact that has on your product, your plant, is that radiant heat is going to hit the leaf. So with HIDs, you tend to have a warmer leaf temperature than you do with a LED light. And we'll talk about that in a little bit, how that impacts our HVAC loads and what we need to size for when we talk about that. But I'm a big fan of the LED light technology right now because one, the price points keep coming down. They keep coming out with technology that, you know, here's a light spectrum that's focused on your veg room. It's good for those small emerging plants. Here's a light spectrum for the flower room. I mean, they are coming up with these types of technology, and you've also got that ability to dim them. You can do sun upping, you can do sun downing to help level out your impact for just, you know, say flipping the switch from going from lights on to lights off. There are a lot of impact there, but I know there are a lot of old school guys out there that still love their HID lights. We're fine with them. We just need to know what they are and how that impacts your crop. That's all. All right, so evapotranspiration is that latent load. So the lighting is the sensible load, meaning the temperature change load. It's adding heat to your room. The evapotranspiration is actually the humidity source. That's where the humidity comes from in your room. If you have a poor system of removing the moisture, then humidity is going to be high and you may not be able to hit your set points. So that evapotranspiration is actually a combination of evaporation, which would come from your soil substrate, whatever that material might be, or it could be from, if you're doing a poor job of watering the plants and you sling gallons of it on the floor, well, guess what? You're going to get evaporation off that concrete surface. That adds to your evaporation rate. So definitely be diligent and don't have a bunch of water on the floor or dripping from the ceiling or whatever. You know, keep that at bay because that will add to your load. The transpiration is actually the process where the plant pulls the moisture up through the stems, moves the nutrients out through the leaf structure, and then the water is excreted by the leaf once it's moved the nutrients. That's the transpiration process. So now we have to be able to move that moisture off that leaf so that the next round of water and nutrients can be pulled up. If we can't get the moisture off the leaf, then it's going to stymie the ability of the plant to take more moisture in.
Paul, do you have a rule of thumb of water in versus water out?
Yeah, actually, I got it right here on the next slide. I mean, water in is water out. We pretty much say, because we're not growing watermelons, day to day, the plant is not retaining a lot of moisture. Now, obviously, the biomass does increase every day, but it's a minuscule amount. So the easiest way for us to kind of calculate and understand that latent load is we just use water in equals water out, because it is that day-to-day, very small changes in the amount of water being retained by the plant. The majority of that water uptake is going to get transpired.
And I think that's one of the common, misconceptions, right? Is the exact amount that's going to come through. I know when I water a plant outside that, the water I'm giving it, that's what it's taking, and that's what it's using to grow. And that's why there's such a huge latent load here, is because that's not actually the case. What we're putting into it is actually getting pulled from the substrate or whatever we're using to water, putting to the leaves, and then moved. And then we have to remove that from the air.
Correct. Now, the other thing to keep in mind is the amount of water that is transpired is directly, related to the amount of energy in the room that can change it from a liquid to a gas. So, this is one of the things that we always look when we at Desert Aire, we've developed a questionnaire that goes out to the grower, and we ask for water consumption, and we also ask for lighting load. How many watts of lights do you have in the room? And the reason we ask for that is because we want to make, well, one, we want to account for the load of the lighting for sensible, but we also want to know, if you're telling me a consumption rate, if you tell me you've got a plant that's going to drink a gallon of water a day, I may call BS on you if you don't have enough energy to actually allow for that transformation of liquid water off of the leaf to a gas. It takes 1,060 BTU of energy to change a pound of water from a liquid to a gas. Now I know, again, the finance guys out there, your heads are spinning, but you got to go back to your high school science, and there's a transformation there. There's a change of state that has to occur. It's just like boiling water on the stove. Water's not going to boil without adding heat. So if you add your heat, it's going to change state. Now, it is also a difference how much pressure is emitted on the top of that surface of water as to the rate at which water will leave. So that's why people always talk about, geez, I went to the mountains and I boiled my potatoes for 40 minutes and geez, they were hard as rocks. Well, it boils at a lower temperature because there's less pressure being emitted by the atmosphere on the surface at a higher elevation. We actually look at the pressure that the air temperature and the relative humidity of the air surrounding the leaf, that creates a vapor pressure, which is emitting onto the leaf. And when it gets too humid, there's not much of a differential between the leaf's pressure and the air's pressure. So therefore, it can't leave. You have a high differential, the water leaves the leaf at a high rate. So yeah, I know I went into probably a little more detail on what some people wanted there, but that is what's occurring. And when we get questionnaires back, we're looking at that and going, and we've got the history now as well to know, if you're giving me a gallon of water per plant, I know there's no way in heck that plant is going to drink a gallon of water a day unless you've come up with some species that is so much different than what everybody else is doing.
Yeah, I'd say several projects that I've been involved in, there's been a decent amount of back and forth on it. Okay, here we'll run it, but here's what you're telling us. This is, you're going to win the Nobel Peace Prize. You're creating energy at this point in time. Let's go back, talk to the cultivator and see, get a better idea of what their watering rates are. It causes them to actually go back and, they were kind of giving you an off the cuff number, and they, do a little study on it, realize, oh, okay, here's the watering rate that I'm actually using.
Well, keep in mind, Eric, that we're asking for water consumption. We're sometimes getting the water rate, and what people aren't keeping in mind is they're not telling us how much runoff they're getting. So a guy might be I'm not doubting he's not putting a gallon per plant into the room, but I think he's failing to tell me that he's collecting in a bucket at the end of the tray. He's recollecting, a half of that or 3/4 of that. And that's the part that, what we're trying to understand is, from a latent moisture removal requirement, how much equipment do we need to remove the moisture out of the air, we truly have to know how much water is getting into the air. And it's got to evaporate or it's got to transpire. So if we have bad information, or if the number we're given is a massive number. Now we have some good tools. We got a tool called Penman-Montath that we're using these days, and we're trusting it a lot more than we used to. But it's a tool that the government put together years ago to effectively estimate the water consumption of different plants in different climates to help people decide what to grow to feed themselves. And so we're getting some great information there, and we've got enough history with the number of projects that we've done. Most of the time we have had projects that are oversized on the equipment more so than they've been undersized. The only time we've had projects undersized is when people say, hey, I can only handle this amount of equipment, or I only have this much electrical load. I'll adjust my plant count accordingly, and then they don't. They throw in plants and they said they were going to, and now the equipment can't keep up. But in more times than not, we end up with more equipment because people have given us a number for the water consumption that isn't realistic or isn't occurring.
Right.
It's less than that. So again, another way to make sure that we're providing the right amount of equipment for the project is getting good data. Okay, this is the picture that's stomata. Again, in the cannabis plant, another tip here is most of the stomata are actually on the underside of the leaf. They're called a dicot because of that. And so if you think about that a second, more of the challenge is moving airflow such that we're getting air into that canopy and under the leaf where most of the water is coming out of that plant leaf. Just an interesting nuance and just another challenge, really. All right, so to better understand evaporative cooling, I like to use this example. I know everybody has been to Vegas or they've been to someplace out west, whether it be Phoenix or Santa Fe or Vegas, and you go to an outdoor bar in the middle of summer and they've got these misters, and you walk in off the street and it's just blazing hot, and you walk into the outside bar and all of a sudden you're like, whoa, this is a lot cooler in here. And you look up and you got these little sprayers and you see all that mist coming out and you're going, well, geez, I'm not getting wet. What's happening? Well, this is the evaporative cooling effect. That water vapor that's being pumped out of those little misters, it's actually water droplets, but before they can actually get to you, they are sucking heat out of that area at the rate of 1,060 BTU per pound of water, and they're changing from a liquid to a gas. And so that's why you don't get wet, but because it's sucking that heat out of the area, it makes the area in the proximity of the mister cooler than the area away from the mister. And this is that impact that we're having inside the room. So here's another tip for you. When you pick your equipment to do sensible cooling and you do it based on the lighting alone, or you do it based on the lighting at the beginning, what happens as the plants get bigger and they start going through more water? Yeah, what happens is those plants and the environment starts absorbing more energy of the light because of that 1,060 BTU per pound of water. So the bigger the plants, the more evaporative cooling that they can do. Now, some people have heard of things called swamp coolers. Swamp coolers they utilize evaporative cooling. So, but they don't work well if you have a high humid air being pushed across, a media that has water on it. How's it going to really absorb any more water? It only works when you have the air around it is dry. And that's why we have to maintain the environment in a grow room at a dry enough condition, at the proper Goldilocks condition, so that it can absorb the moisture off the leaf and keep that happening continuously. Okay, so when we talk about the lights on, you're going to have that high sensible heat from the lights. You're going to have the latent load from the evapotranspiration, and you're going to have that sensible cooling effect from the evaporation, the evaporative cooling effect. The bigger the plants get, the more water they're drinking, the more evaporative cooling you get that offsets the sensible heat from the lights. So when we're in the lights on, we're going to need cooling, just temperature change, and we're going to be needing dehumidification. Now at the beginning, cooling will be highest when the plants are small, but then as the plants grow, the sensible cooling need will drop. And as the plants grow and they drink more water, the latent moisture removal goes up. So at the beginning, when the plants are going in at, say, early flower, you don't have as much water consumption, but you don't have as much evaporative cooling. So you have a higher sensible with less latent. But over that 8-week flower room period, your sensible cooling need is going to go down and your latent moisture removal from dehumidification is going to go up. So it's dynamic, it's changing, and it changes as the plants change. Now when we switch and go over to lights off, when lights off, you don't have photosynthesis. And without photosynthesis, the plants really don't drink. Now there are some equations out there that say that they will continue to absorb some moisture at nighttime and will continue to transpire, but it's at a significantly slower rate. I think I mentioned earlier the Penman-Montheth equation, and what we use at Desert Aire is for flower rooms, 75% of the water that's consumed by the plant occurs in that 12-hour lights off period. And only 25% of the water consumption for the day is transpired during the 12-hour lights off period. So if you made an assumption, or if your engineer made an assumption that, geez, I got a 24-hour day, I got this much moisture removed, divide it by 12, and didn't apply the factor that only that 75% of it's going to happen in the lights off, you're going to be undersized in your lights on period. The other side of that coin is if you were relying on your air conditioner to remove moisture during lights off, why would the air conditioner even run without the lighting load? It won't. I mean, unless there's some sort of heat gain coming from the external walls or somewhere else in the room, we don't need to be adding much cooling, if at all any, during the lights on period. So our primary load with lights off is going to be a dehumidification load, and only a dehumidification load. Now, possibly it could need some heat, and that's where it comes in, us understanding that heat loss equation. So take a winter month and you've got external walls. You have say you've got two external walls on this particular flower room over in the corner of your building, and it's 10 degrees outside. We could see the temperature in the flower room during lights off drop rather dramatically if you don't have a good insulation on that. And that's why we ask for, do we have any external heat gain or heat loss? All right, well, now that we kind of set the stage for what goes on in the grow room, what we want to talk about is how do we do it efficiently? How do we select efficient HVAC? So, in the lights on period, we talked about the need for sensible cooling and for dehumidification. And in the lights off mode, we talked about dehumidification only and possibly heating. So let's check. So comfort cooling equipment, and just so everybody understands what I'm talking about when I say comfort cooling. So anything to do with, say, a standard commercial building HVAC, a packaged rooftop, a packaged air conditioning rooftop, a VRF system, a data center type of unit, anything that is sized to do temperature control as its primary function is kind of that comfort cooling equipment that I'm speaking to. And so if you compare the needs for comfort cooling, an office environment, your operating modes, you're going to have an occupied and an unoccupied. You're going to have points in time where you're there and you want to condition, and when you leave at work at night to save some energy, you raise the temperature in the room a little bit during summertime. You don't want to cycle the cooling as much. You want to keep the electricity consumption down. So you change the set point. Your lighting is typically, 0.7 to 1.2 watts per square foot. Space temperatures 70 to 75, 50 to 60% RH is a nice comfort zone for commercial buildings. There is an outdoor air requirement for commercial buildings. Again, I spoke to this earlier. ASHRAE 62.1 is the code ventilation requirement for commercial buildings, so that we don't choke on our own fumes. And certainly now during the coronavirus thing, people are talking about, do we will we be changing that ASHRAE 62.1 code requirement to bring in more outside air for the occupied space? Yeah, maybe, right? And then carbon dioxide, effectively, we're getting diluted through the amount of ventilation air that we bring in. But now we start talking about cannabis and indoor plants, whether it be lettuces or cannabis, but I know you guys are the cannabis crowd. We have lights on and we have lights off, as opposed to occupied, unoccupied. The plants are there both times. We just change the loads rather significantly. Lighting is going to be somewhere between 30 to 80 watts per square foot. For instance, I know the state of Illinois, I think, has put a requirement in that your lighting load cannot exceed 36 watts per square foot. What they're trying to do is drive people to more efficient lighting methods and keep the electrical grid somewhat in check. I know the state of Massachusetts has a condition, I think it's 34 watts per square foot out there, and they've been very successful in keeping the energy consumption down in some of the grow rooms because of what they're trying to drive on the lighting requirement. Space temperatures, we're going to see anywhere from 65 to 83, and then, you know, you guys are kind of across the map. You know where your secret sauce is, where your temperature and humidity may be through this cycle. I mean, bedroom, you tend to be a little warmer, maybe that 82, 83. You can be a little more humid because you don't want to just have that plant dry out. You're trying to retain some of that moisture so it can actually produce more biomass. When you get into the flower room, you know, you're going to be maybe in that 75 to 80 degree temperature, you know, at that 55 to 65 sort of relative humidity. And then there is no ventilation requirement. And again, if you did have ventilation, how does that impact CO2? I mean, one of the things that we've talked about with CO2, we're doing CO2 injection into the cannabis rooms because people have figured out that CO2 absorption, when it's at a parts per million of 1,200 to 1,500 parts per million, you get better plant growth. You get a quicker plant growth. So normally occurring CO2 is about 400 parts per million. So if you bring in a lot of ventilation air, you're going to go through a lot more CO2 trying to maintain a higher CO2 level. So certainly that's a big difference between the comfort cooling side of the equation. So there are some significant differences there, and you know, as we get into it, you'll see more about it. When we talk about the, you know, inefficient method to do a grow room, it's really the cheap method. It's buying an air conditioner and then buying portables. They are easy to install. They are cheap first cost. You can typically find these off the shelf. That just means you're not doing planning very well if you're just trying to get the first thing available in the market. But, you know, the big impact here is you're going to have higher operating costs. Air conditioners are not efficient at moisture removal. They're good at temperature control. That's what they're sized for, but they're not good at moisture removal. So you got to look at what you're trying to accomplish. If you're going to try to throw these into your money room, which is your flower room, and that's also the high latent load, is that the right product for you? And then we start talking about these portables. Most of the portable units that people are using these days, they reject their heat to the space. So what I mean by that, if a unit takes 75 degrees into it to remove moisture, the leaving air temperature of that will probably be about 95. So now you're putting heat back in the room from this operating unit. It's not connected to something to reject the heat from compression. So, you know, the more these run, the more heat it puts in a room. That becomes very inefficient because now this air conditioner has to run more frequently to keep the temperature down. So what we find is operating costs with this method are more than if you had a purpose-built, temperature and humidity machine.
Well, and how do you get those two to work together in tandem, right? I mean, you're two independent units at different control points and.
Well, and we always say, we've had guys that they'll have 20 or 30 of these portables in a room, and there comes a point in time where they want to change the set point. Now what? They're going to go around to 20, 30 of those in each room and make a lot of adjustment. They're not working together. They're working independently. So again, you can elect to do that, but that's another aspect of this business that over time, labor is going to be a significant impact to your ability to grow, to your growing costs. So if you're spending labor to hand water, if you're spending labor to go and change set points manually and not be automated, you're probably going to see yourself not as cost effective as somebody else who does.
Well, and you mentioned that through the 8-week flowering period that, you're basically it's changing, right? It's not like you're going to go in and set
Right.
it once and it's going to be fine. I mean, what you're doing this week is going to change from what you're doing next week. So it's not like you're ever going to encounter the time where you don't need to change the set points.
Yeah, we've started asking people, especially for the flower room, typically 4 different windows of temperature control and humidity control through that 8 to 9 week flower room. When the plants first go into that flower room, there may be a transition period from veg to flower where they don't use the full lighting impact because the plant can't absorb it all anyway, so why waste it? And they tend to be at a little warmer temperature as they're getting acclimated to this new room. I mean, again, they moved the plants, so they're trying to get them acclimated. They might do that for a week or two, and then you start changing the temperature and the set point as that plant starts getting bigger and going through its load. And then the other thing is people like to change the temperature towards the end of the cycle because they're trying to direct that plant to focus on the flower and produce more resin. It's that end of life. The plant will actually create more resin, more sticky substance to try to collect pollen. They haven't pollinated yet, so the female plant's trying to figure out, how do I collect pollen? And it just starts really impacting there at the end. And plus you're looking at, some of the guys are looking to dry the plant out a little bit, so they'll actually cut a lot of the biomass off that doesn't have flower on it. So the photosynthesis quantity goes down because there's less biomass, so they can actually move the temperatures down a little bit and not affect what equipment they sized. So a lot of that, it's a complicated deal. You have to take it all in consideration. So here's an example of a project that we worked on at Desert Aire several years ago. The first phase was done with portables and air conditioners. And this is if you're not familiar with it, it's a 4-day trend line, trend graph. Temperature is in the top, and relative humidity is down on the bottom. But the yellow is the lights on period. The white is the lights off period. So you've got 4 cycles here, 4 days, 4 24-hour periods. And you can see they were trying to maintain 75 degree Fahrenheit at about 50%, 52% relative humidity. And you can see that they did a piss poor job of doing it. I mean,
way off.
Yeah, I mean, this isn't even, I know it's kind of hard to see, but this is 90 degrees on this band up here, and here's 70. So there's a 20-degree span, and they're even going outside of that on the 4-day window. And the relative humidity is going everywhere from as low as 25 to as high as 85%. Now, we all know that relative humidity does change a little bit, does change with a change in temperature because it is relative, but it's not a stable environment. This particular grower sought us out for his phase 2, and we installed Desert Aire equipment, which is purpose-built with, we control temperature and humidity, moisture removal with the one machine. And we'd like to do 2 machines that work together in a room so that we have more stages of operation. And this is what his facility looked like afterwards. He's maintaining his temperature, and you can see now there's a little blip there. And where the blip, what causes the blip? Guess what? Lights on to lights off, right? Or lights off to lights on. You have this huge temperature change done with the flip of a switch. He didn't do any sun downing or sun upping. He just turned the lights off. And when it came time to turn them on, boom, they were all on. So that's why I say, some of the benefits with LEDs, being able to do changes in intensity, being able to do that sun upping over 30 minutes or sun downing over a 30-minute window would actually level out these little peaks. And in dew point, which if you have stable dew point, this is absolute moisture. If we have stable dew point, we have stable VPD. Now, we haven't talked about VPD yet, but that's vapor pressure deficit, and that's an absolute moisture issue. And this is telling me I have a stable temperature and I have a stable humidity. So I've got an ideal climate to maximize my growth. This guy indicated to us that his growth rate, his yield increased 25%. I mean, he paid back our equipment within a year. He was a fan. So I'm bringing it up just because that's something you have to look at. Yes, I'm more expensive than that inefficient product, but if you're in this for a few years, why not do it right and try to keep your costs down? So let's take a look at purpose-built product.
In a closed environment, you're providing everything. Proven methods, proven supplies.
We want to have that perfect day for everybody.
This is not new energy, this is energy that the customer has already paid for.
The ability to control the sensible and latent loads independently within a space allow it to be a one-stop shop for the perfect condition.
With a commercial greenhouse, you're basically supplementing what Mother Nature's already providing. In a closed environment, you're providing everything. You have the ability to provide the perfect day.
The biggest thing growers need to understand is that there's a process and there's time that needs to be sat down and really plan out what you want to do on any type of project. There's a lot of ways to build one of these type facilities. You want to put the technology and the equipment in that makes the grower most comfortable in his style of grow, and remember the market that you're growing for. Those are the key things. You know, we want to have that perfect day for everybody.
Mike Miller from Fluid Transfer Products has supported our goals by keeping us connected to the understanding of the equipment. I mean, there's a lot of relationship there to understand what it is we're trying to accomplish and to be able to communicate that with him so that he can have that equipment do just that.
FTP is, we've been in business now for over 30 years. Our involvement in this particular project was to gather all the data necessary, both in the fact of do we have a controllable space, what are the design conditions, plant count, things of that nature, so that we could actually make sure that we had a controllable space and that we had equipment that was sized properly to maintain the conditions, both the temperature and the humidity in the space.
And the nice thing about Desert Air equipment is when you get in these kinds of environments, we have to do a lot of factors. We've got to heat, we've got to cool, and we've got to dehumidify. Desert Air has the knowledge and the ability to do that in all in 1 year.
The Desert Air Grow Air system is a fully integrated system that controls dehumidification, cooling, and heating all in one package. The ability to control the sensible and latent loads independently within a space allow it to be a one-stop shop for the perfect condition. AirGuard helps our users by allowing us access to their system to answer questions and identify any small issues that might occur. In this case, there were plenty of questions that were coming from Griffin and Revolutionary clinics that we were able to answer on a remote basis.
Some of the qualitative results that we've had achieving the perfect day environment is being able to stay within a set of parameters. When we set our temperatures and our humidity, we're staying within those. In the past, when I've tried to set parameters, it seems like there's really big swings up and down. We've been able to fine-tune that.
One of the neat features of the Grow Air unit is that it has a full-sized hot gas reheat. The hot gas reheat is using energy that was absorbed through the evaporator coil, both the sensible and the latent, after we've dropped that temperature down to remove the moisture. This is not new energy, this is energy that the customer has already paid for basically in the facility that we're using, and negates the need for any type of new energy or additional
At Desert Air, we
costs
do
associated
a
with
purpose-built
providing
product.
that.
We originated back in 1978 as a dehumidification-centric product. I always tell people, yeah, we're in the HVAC industry. We do not make air conditioners. We make dehumidification systems that control temperature. And that's the big difference. Yes, we have compressors, so do Carrier units, so do York units. but our compressors are used for moisture removal and then temperature control, whereas the air conditioner family out there, they're doing temperature control, and then it's, oh, by the way, I have a little bit of moisture removal I can provide to you when I'm running based on temperature. So my units run based on whether there's a need for temperature, or they run based on whether there's a need for dehumidification. We have this thing called a modulating hot gas reheat coil, and it's full-sized, and that allows us to rewarm the air that we've cooled in order to remove the moisture out of the air. We get to rewarm that air for free. It's energy we've already spent. We're not having to fire up an electric heater or a gas furnace to bring the temperature back up after cooling it down to remove moisture. So again, another energy efficient method. So that's what we're doing. And again, we've got these units that we can do as indoor, either air-cooled or water-cooled units. This is a room, the one in the background is a project over in Massachusetts. These two units are working together for this little flower room on the other side. This was a 4-story shoe factory that was about 130 years old, that the grower bought for a very inexpensive price in downtrodden western Massachusetts. And so we're growing product on 4 floors. So now they're not air-cooled units, but they're water-cooled. He's got a water line running around to it, and we're just rejecting our heat. Whatever waste heat we have from the equipment is being dumped into that water loop that goes out and then is being cooled by a cooling tower. But you know, we can do these as air-cooled, water-cooled, but these two units work together to maintain that environment on the other side of the wall. This project here down in the foreground, these are our units on the roof. They are air-cooled packaged units for dehumidification and temperature control. And you can see there's a whole slew of those bad boys. These two here are working together. The next two are working together. The next two, I think there's probably about 30 of these units on that project. Again, you know, it's where do you want to put the equipment is what that comes down to. These both operate the same way. These up here in the background are a little smaller, but we also have sizes up to this size. This guy here just wanted to put his units on the roof. He didn't want to take up space inside the building. The folks here in Massachusetts, because they were on 4 stories, if you can imagine, if you tried to put stuff up on the roof, how do you get the equipment? How do you get the airflow all the way back down to the first floor? It would be cumbersome to try to run ductwork up and down to do that. So, and the other thing is, this equipment will operate year-round. We've got equipment that's outdoors operating up in Alberta, Canada, and it gets to minus 40 degrees Fahrenheit in the winter. And this equipment is operating. Now, I know most of the folks, yeah, of course it operates. It's heating. Well, no, it's not. It's dehumidifying. It's the refrigeration system is operating. Air conditioners aren't meant to operate in the dead of winter. Now, some are if they're data center type units, but a data center type unit doesn't really have a need to remove a bunch of moisture. So think about the origin of the product that you're considering, and what was its intended purpose, and what's your purpose. I think that's the best way to try to explain.
All right, guys, I think that wraps it up. Shoot Eric an email if you guys have any follow-up questions. And again, utilize our website and Desert Air's website for more information.
Thanks a bunch, guys. Appreciate it.
All right,
guys.
thanks. Have a good one.